guys, this is an off-the-cuff video. This is a video response, and also not that response, but an addition, an appendix to the awesome video that Hussein Nasser did yesterday. So his video is about how many kernel systems calls do runtimes make, and he puts the numbers down here. Python 662 system calls, Node 800 system calls, Bun 950 system calls, and unsurprisingly, C makes only 47 system calls. So I looked into the numbers and I wanted to understand what this meant. So let me show you what I'm talking about. So, oh, by the way, please go watch Hussein Nasser channel first. He's an awesome content creator. I actually look up to him a lot. And yeah, so the long story short is that he has an input file, and then what he does is reads the file, prints it to the console. To get the number of system calls, oh, well, what are system calls? Well, system calls are pretty much calls to the kernel. Pretty much all the useful stuff happens in the kernel. So whether you're talking to a device, or you are writing to a file, or you're allocating memory, well, that's all system calls, right? He shows that he uses sudo strace to do this. And let's go ahead and compile our C program first. So GCC. Okay, we compile our C program, and then we are going to strace that. But strace with a C, I think, so that it shows us the summary of the system calls. I'm connected to an Ubuntu computer, by the way, even when I'm using macOS. So I'm able to reproduce the number of calls that he got, more or less, you know, close enough. Okay, so we got this number of calls in C. Let's create a similar program in Rust, which I prepared beforehand. You'll see that there's a lot of commented code, but I'll get to that in a second here. Obviously, when I build it for release, and then sudo strace, and we are going to strace target release system calls. Okay, so we get 98 system calls. So I want to just tell you straight up, do not take this number and say, well, it's about twice as performant as Rust, because it makes half the system calls roughly. This is a very simplistic point of view. What we need to do is how expensive these calls are. What are we doing? Like, do we get something out of these extra system calls that we are doing in Rust? If you ask ChatGPT why you have more calls in Rust, it will tell you that, oh, it's because the type safety and because the borrow checker and all this stuff. And I'm like, that doesn't make any sense. So I decided to dive a little bit deeper here. And what I did is I said, well, what happens if I comment out all the code? Even without any user code, Rust is at 89 calls. So this means that there's something else going on, something that is set up by the frameworks, not by us, that is consuming all these system calls. And maybe it's a good thing. This is something I want you to walk away. Less calls does not necessarily mean the system is worst. Too many calls, that's bad, because you're switching between kernel space and user space, as Hussein clearly explains. But it's a very simplistic, it's a very superficial and dumb measure to just say, oh, more system calls, the worse the runtime is. That's not fair. So I said, all right, can I see what these system calls are actually? And the answer is yes. You can remove the -c, and here you see the raw system calls. Let's compare the system calls with what we get with C when we remove all our code. Okay, so now we have apples to apples here. Maybe there are some checks and there are some things that Rust does for us. We see that the first call is the same. So this, as we mentioned, this is to begin execution by calling execve, which loads the executable. That makes sense. Both do it. Next call, brk. This is part of the memory management setup. brk is called to query the current location of the program's heap. The memory layout is being set up by the operating system for the process. So both do the same. And then they both access these ld.so preload. We know that that's to preload any shared libraries that the system, that the application might need. So far so good. Looks very, very similar. Then open at. This opens the shared library cache, which contains a list of all shared libraries available on the system. So very, very similar stuff. But then we notice that there's a critical divergence of what's going on between Rust and C. This is the only shared library that we are loading, while in Rust, we also load the threads library. Right? Yeah, so we also load this pthreads library. The C program does not set up signal handlers or manage thread local storage explicitly unless it's part of the code. In contrast, Rust runtime automatically sets up signal handling. That's when you press Ctrl+C and the program dies, and threading infrastructure. So that's why we need to load lib pthreads. With regards to memory management, the Rust runtime more robust memory management results in more mprotect calls for enforcing memory protections. C program often rely on you, the developer, to make the application crash often. The C program produces fewer system calls overall because it relies on a simpler runtime, loading only bare minimum libraries, so it's mostly libc, and performing minimal system level configuration. In contrast to that, Rust runtime introduces additional safety checks, thread setup, and library loading, which results in more system calls, especially for memory management, threading, and signal handling. Even though both programs achieve similar goals, they do nothing. Rust runtime takes on more responsibility to ensure safety and robustness, reflected in the number and variety of system calls. And here's one particular nugget that will be very, very interesting for you Rustaceans. In case of Rust, we see that all Rust programs subscribe to RT-SIG action. And reading about it, this is just so that when there's a fatal exception, like a panic or something, Rust has always a chance to catch that signal and unwind the exceptions. Unwinding, what do we mean by that? It's cleaning up the stack trace so that we just don't leak a bunch of memory. Because if you leak all that memory, think Windows 95. What used to happen is all programs leaked memory, and then because they didn't clean up properly, the OS was not able to reclaim all that memory back. And then what did you have to do? Just reboot. So Rust is trying to protect you by adding all these signal handling. The conclusion here is think past the simpler stuff. More calls does not mean it's worst. It just means it does more stuff for you. So if you're into Rust, I'm sure that this video will benefit you. So check out this video here, and yeah, have a good one.